Okay, well, almost forgot about nuclear power, so we actually have two short videos on nuclear power before we sum up our section on non-renewable energy. And so we're going to spend some time kind of introducing what nuclear power is, how it's used. So we've discussed fossil fuel emissions, that they pollute the air as you combust them or burn them. That's kind of the biggest impact of fossil fuel use, is all that mostly greenhouse gas going into our atmosphere, this huge release of carbon dioxide, which you can see the chart down there at the bottom, is just continuing to go up and up and up. And you saw in An Inconvenient Truth, Al Gore's video, how that is having a major impact. Our carbon dioxide levels, which is a greenhouse gas, are at all-time record highs, and they continue to go up. And these are a result mostly of the fact that we continue to burn fossil fuels for our primary energy sources. Um, it causes, in addition to causing climate change, it also causes a lot of health problems. You have, technologies, you'll hear Obama talking about clean coal, low sulfur and all that. And yeah, it helps a little bit, but you never reduce the amount of carbon dioxide. And that's kind of the big key player, as you saw in Inconvenient Truth. That's the big problem we're talking about. Well, we have nuclear power, which is, somewhat of an alternative, and you've actually been hearing quite a bit about nuclear in the media lately. So what exactly is nuclear power? Well, if you remember back to what an atom is, at the center, the nucleus of your atom, remember an atom is the smallest unit of matter. At the center in the nucleus, you have neutrons and protons, and then you have electrons whipping around in circles around that nucleus. And so there is basically a force that holds inside the nucleus the protons and neutrons together, and that force is nuclear power. That's where the word comes from. Nucleus, nuclear, the power within the nucleus holding the protons and neutrons together. And it's actually a massive amount of power depending on the atom that you decide to try and harness that energy from. Now, how do we get at that energy? We use a process that's called nuclear fission. So there's two words to be familiar with here. Fission, think of fissure, a fissure in the earth. A fissure is a splitting apart of. So we're basically splitting an atom in half to harness that nuclear power. Nuclear fusion, fuse is fusing together, putting together. So it's not fusion, it's fission. We are breaking apart. Okay, so this splitting apart of the nucleus, this think fissure, split, or crack. Now, the heavier the atom is, the more protons and neutrons there are in it, and that means the more power there is. So we tend to use really heavy atoms like uranium and plutonium as our primary elements used in nuclear power because they are such heavy, heavy atoms, meaning they have really high atomic numbers, which means they have a lot of protons and neutrons, really big nucleus, which means there's a lot of power in there that we could access and harness. Now, when the nucleus splits, it gives off this immense amount of energy, and it gives it off in the form of some of its heat, some of its light, and some of it is radiation. As you know, uranium, plutonium, we're working with radioactive elements here. And this is all released as these neutrons get pop off and get broken off from the nucleus. And so what you end up having is a chain reaction, a major positive feedback loop that can get snowballing out of control really quickly. So one of the biggest things with nuclear power is you have to keep it extremely under tight, tight, tight control because it can very quickly escalate out of control. And you've seen that in the media. So again, must be highly controlled because it quickly gets out of control. This is why nuclear power is so risky. Now, how do we control that? Well, the reaction is controlled by only allowing one of the 2 to 3 neutrons that are released during nuclear fission to go into the next reaction. So basically what happens, you're going to see a picture of this in a second here. Let me just keep going and then we'll talk about it. The neutrons, in addition to not only reducing the number allowed to go into the next reaction, they are also slowed down because at the rate that they're going, they're so fast that they would just rip through the atoms. So we slow them down so that they can break apart a nucleus, and they use the medium to slow them down. They use water or they use graphite. And then the excess neutrons that they don't want moving into the next reaction are soaked up using these things called control rods. Now, we're not going to get super technical in this class. None of us are nuclear physicists, so, unless you're planning to go into nuclear science, then by all means, you're going to be taking a lot more classes than this one. So here's a picture to kind of give you a visual of what's happening. At the very top, you see that tiny little red dot at the top. That is a neutron. So the neutron comes in and it slams into the nucleus of a uranium atom there. It slams in and you see nuclear fission happening where you get two smaller nucleus. So the two smaller nucleus go off in opposite directions. You have that blow up, that little thing that looks like a sun almost. That's your energy being released, your light, your heat, your radiation. And then you've got kind of some leftovers. You've got these three kind of wild neutrons that are being released. And then those three neutrons, if not controlled, would go to break three more nucleuses. And then you'd end up with, three from each of those. So then you'd have 12. And then after that, and you see how it exponentially gets out of control. But so this is the idea of why it's a positive feedback loop that has to be extremely controlled. They will go in here and they will only allow one of these three to go through. The other two will get sucked up into a control rod. So how does a nuclear power plant work? Well, it basically operates the same as a coal-fired or a natural gas-fired power plant. You have a nuclear reaction going on kind of in the core there, which would be, the same thing as the furnace burning. So you've got this nuclear fission going on in this contained vessel. That's creating a lot of heat. So that heat is then used to boil water. The steam being released from the boiling water goes up into a turbine. It spins the turbine spins a generator, the generator creates electricity, and that electricity is captured and sent to the grid. So this is kind of what it looks like. The same idea. You've got over on the left-hand side, you see the red and the yellow sections. You see your control rods, the nuclear reactions going on inside that reactor vessel. All the heat and all that is being taken in, and the hot pipe that's going into off to the right there, you see kind of the big vessel holding the water, and that's the water that's being boiled, the steam going up into the pipe, going in, spinning the turbine is connected to the generator spins where the magnets spin around a copper wire, creating a movement of electrons, which is electricity. It's captured and sent off to the grid. Now the steam is also just like in the other the other power plants that are coal and natural gas fired, the steam is condensed back down, cooled down, back into water, and sent back through the system again. So same kind of concept. So let's talk about nuclear fuel. The fuel that is used in the United States is uranium. We use uranium here. Other countries use uranium as well as plutonium. We don't use plutonium here. Now, uranium is a naturally occurring element. It's just like phosphorus or sulfur. It's in rocks in the ground. And so, how do we obtain it? We have to mine for it. And as you know, mining takes a big toll and has a major footprint on the earth. Now, when we mine for uranium, there are different isotopes of any element. What I mean by that is elements can have varying numbers of neutrons in them. And so there is the atomic number there, that 238. Uranium 238 is mostly what we get when we mine, and that's indicating the number of neutrons. What we need for our reactors, though, is uranium 235, which is a slightly lighter uranium. It has three fewer neutrons in it. And being smaller and lighter, not having as many neutrons, means that it doesn't take quite as much energy to split and go through that nuclear fission. So, and that's what I just explained there. So when we mine for it, 99% of the uranium that occurs in nature, though, is uranium-238. Less than 1% of it is uranium-235. So what we have to do is we mine the uranium and then we have to filter out the non-usable stuff. So there's an incredible amount of waste created, all these huge tailings, when mining for uranium. It's not, a simple process. And of course, doing all of this filtering and all that, it uses a ton of energy. So then you're also, of course, using energy to get the fuel to use to make more energy. So there's always that to take into account. Now here's what uranium looks like. They send it in a pellet form over to the reactors. So up in the upper left there, you see the uranium pellets. And then the fuel rods are basically filled with those pellets. So off in the upper right, you see these rods. The rods last about 3 to 4 years, depending on how often that power plant is being run. Now, on the lower left there, you see kind of those metal spears sticking up. Those are the control rods of graphite or of water, whatever, probably graphite. And that's used to absorb those neutrons that they don't want going into the next reaction so it doesn't get out of control. So in between those are the fuel rods. Now here's what uranium extraction looks like when they're mining for it, these huge, huge tailings. Basically what they do is they drill down these wells where they know uranium ore is, and they send in this leaching solution. And I'm not sure exactly what's in it, but I could guess that it's rather chemical filled and toxic and not real good for anyone because you're basically leaching a metal out of the rocks. And so that leaching solution is going in, leaching the uranium out, and then they put in kind of a well in the center where they're basically sucking all that liquid back up, and then they're getting the uranium out of that leaching solution. Now, nuclear energy byproducts. Well, the mining waste, you have about, for every 1,000 tons of uranium, it results in 100,000 tons of radioactive tailings or mined waste. Excuse me, mine waste, not mined. My mind is wasting away. 3.5 million liters of liquid waste. So a massive amount of waste for a small amount of fuel. Now, the electricity production waste, after the uranium goes through nuclear fission, you're left with plutonium. Now, I said we don't use plutonium here in our nuclear sites, but other countries do. Now, the thing is that even the byproduct, that what your end result, once you've gone through nuclear fission and uranium is split apart, now you have plutonium, it's still radioactive. It's even, in fact, more radioactive than uranium, but it has a shorter half-life, meaning that it lets go of that radioactivity faster than uranium does. For example, plutonium's half-life is 24,000 years versus uranium's half-life, which is 704,000 years, which means that it's going to get rid of its radioactivity much faster, so we don't have to store it nearly as long. Now, again, some countries reuse the waste, we don't. Now, in this next one, we're going to go more in detail about the half-life and the storage. I do want to real quickly go back here and mention, hang on a second here. Oops. The nice thing about nuclear power is that there is no carbon dioxide being given off. So this is the real pro with nuclear. You can see in the power plant here, you've got your heat, but it's all contained within a vessel. There's no carbon dioxide, there's no burning going on. So you don't have any of these greenhouse gas emissions getting out into the atmosphere. So that's the pro of nuclear fuel and using nuclear power. Basically, the only byproduct is some water, but you have all the mining waste, the tailings, the half-life, and the storage, which we're going to talk about next, that you have to deal with. So that's why nuclear power initially is extremely attractive, because you don't have all that carbon dioxide, but you'll have to keep in mind all the steps it took to get there, not to mention how extremely dangerous the reaction is and how quickly it can get out of control. And when it does get out of control, you get some really big consequences, and we'll talk about that in the next lecture as well. So stay tuned for that.